So today also we'll continue with our lab sessions. So we'll try to figure out the W by L ratio, typically the L value. Now, how do I want to figure out the value of L and what is the importance of that? Let's try to understand that. Now, to do that, again we'll take up a simple N MOSFET, and thereon we'll try to fix up the value of L, that is the length. And from next experiments onwards, we'll be using that sort of W by L to ensure we are getting the proper outcomes. Okay, so I'm in my cadence tool. So let's try to create a new cell view because I have already created the library. So which is my tutorial underscore one, or maybe in the tutorial new. So let's create a new cell and MOS length calculation, something like that. Let's say okay. So this window will pop up. Okay, so let us try to place all the components. So let us place first the NMOS. How do I arrive at this window? Add instance, I'll press I. So the moment I press I, I'll arrive at this instance. I'll browse and I'll go to where will be my NMOSFETs, all those things will be located. It will be in the NMOS. So I want to take NMOS 1B. Symbol is being selected out here. Then I'll ensure that the value of the default values, whatever you are having over here, will fix up the default values for the width, but for the length, I'm going to consider the value as variable because I need to find the value of L. So this is, I'm putting the variable here. So let's do that. You see, L is being mentioned by the variable capital L. So again, let's add all the sources. So sources will be available in the analog lib, and I want to add one AC source and a DC source. AC source is towards the drain side so that it helps me to find out the output resistance, and based on the output resistance, I'll be able to find my length. Why I am taking that? Let me make it clear. So we sign, yeah. So in that DC voltage, I'm going to keep it as 0.9. AC magnitude will be 1. Then I'll keep VDC with a magnitude DC voltage of 0.9 or 900 millivolts. So that will be at my gate side. So let me connect these things. Now the reason being choosing AC source again at the output side here is, since in my next experiments I am going to use current source. That means I want to build, if I want to build any sort of amplifier, I need biasing circuits for those amplifier. Basically, what is the role of the biasing circuit? It helps my MOSFET to stay in the saturation region, and to do that I need to add some additional circuits. As simple as that. If I want to ensure my MOSFET or my entire MOSFET circuit is in the saturation region, I need to ensure that these particular MOSFET has to be in the saturation region. And the best part to make sure the MOSFET enter into saturation region is to ensure that the output current or the current flowing through the MOSFET remains constant. That's how I can make my MOSFET to stay in the saturation region. If I want to ensure a constant current has to flow, or basically if I want to ensure that current, the MOSFET has to generate a constant current, then the best way to ensure biasing happens is to build a simple current source, so that that current source itself I attach it to my MOSFET. That means that my MOSFET will be always giving the constant current. So to ensure that I am attaching a current source, I cannot use the normal current source like IDC or iSine in building my circuit, because normally when it goes for the fabrication, you cannot always use the typical current sources because those current sources are bigger in size. So you need to develop some current sources using the MOSFETs only. And there comes the concept of current mirror. So current mirrors or current sources, their job is to ensure whatever the reference current is there, it will be mirroring those currents. So in order to ensure that the current source is generated, I need to first build the current mirror. And in order to do all those sort of things, I need to establish certain condition. Condition is what? The condition is the output resistance of any current source. If you take the resistance of that particular current source must be as much as high as possible, practically speaking, or in terms of idealistic value, the output resistance of my current source should be ideally infinite. So that means if I want to build a current source, then that current source output resistance has to be very, 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 very large. And that if I want to achieve, that means I need to first figure out a particular length for which my output resistance of a MOSFET is very, very large. Then if whatever the value of L I am going to get, for that L, what is the value of R? That R should be very, very large. Now, if I use that particular R, or if I use that particular L in building my current source, then that current source will be developing a constant current whose output resistance will be very, very large, because you have chosen the value of L according to the resistance which you are calculating over here. So basically, you are putting in the AC supply over here, which is going to act as an input now. Now here, if you do V by I, whatever the value of R you are going to get, that will be your output resistance, because you are attaching the source towards the output. So once you do that, see, when you are applying the source over here, you are applying the source at the output side. And that means it is going to generate some voltage and there is a current. You do the division of that, you are going to get the resistance. That resistance is the output resistance. Now that resistance has to be very, very large. And how your resistance is connected with your R, you know that. Let's just, I'll just, yeah, take up here. So we have already seen that. Let me just give you simple just on how your R is dependent on which all parameter. We have already seen. So we know that. Hold on for a minute. Okay, no, it is not. I'm not able to write it. Okay. So basically, we know that. Okay, let me just give you a small glimpse. So basically, we know that, or else, let me just take this expression out of here. Yeah, that's okay. So we know that ID equation in the linear region basically is given by UN Cox W by L. I'm just trying to give you the dependency of R on which all parameters or how we calculate it. 1 by 2 VDS square. This is what we have the equation. Now input, basically VDS, this VDS, it will be very small in linear region. Okay, so now I am trying to give you the value dependency of RDS on different parameters, and that's why I'm taking an example of ID equation in the linear region. So if this is very small, here will be an equation. So this will be very small. So VDS square term will be even small. So I ignore this. So I'll bring this down over here. So what I got ID by VDS equal to mu n Cox W by L VGS minus VT. So if I have all those things, so what is my R? R will be the inverse of that. So basically your RDS will be 1 upon, I can replace mu n Cox with K W by L VGS minus VT, and K is constant, VGS will be constant, VT is constant. So if I want to establish a relationship between R and W by L, I can say that RDS is proportional to 1 by W by L, or I can say that my RDS is proportional to L by W, or indeed I can say that RDS is proportional to L. So basically, I just wanted to see, give you the establishing a relationship between the resistance and the length. So that's the reason I'm taking my length as variable. Now, why your why the question why you have taken the equation in the linear region is because to establish a relationship between the resistance and length, I have taken the equation in the linear region. That's it. Nothing more than that. But our entire MOSFET thinks whatever the MOSFETs you are working, those entire MOSFETs would be working in the saturation region only. But because you have given, see, here is your input. Now you have given the input over here. So that's why when you give the input, that input is your VGS. I mean, basically that is the input which is of very small signal. That's why you took the equation in the linear region and then you established the relation. So relation says what? Your resistance is directly proportional to L. That means and when your length increases, your R increases. Now, what is the limitation? To what extent should I increase the value of R? So let us try to calculate the resistance by doing some parametric sweep. Or basically, I'll just try to vary this L, and across different value of L, let us try to figure out what will be the value of my resistance. So let us try to calculate. So once, okay, there is an error. Okay, body I have not tied. This has to be tied. Okay, launch ADL. So I have created a variable. So I'll do copy from cell view. L will come. So initially, let's consider. So what is the value of W we have fixed? Okay, let's first do that also. I'll fix up the value of W, not the default value. So let's fix up the value of W to some 10 micro. So that for calculation, it will be easy. Then I have L. So let's start varying the value of L. So let's start to vary. So first, let us fix up L equal to 100 nano and do the analysis. So what is the analysis? Since I am putting the AC source over there, I'll do AC analysis. I'll vary it from 1 to 100 megahertz. Let's say okay, and then I'll plot the current, drain current, press escape, and then again I'll move back to this window. This current came, then I'll run this. Now for this value of L, W is already placed in the window. So this is my ID versus VDS in terms of frequency. That's why I can see across all the frequency. So now to get this RDS, so it is basically I by V. So I want V by I. So I'll just send it to the calculator. I'll take the inverse of that. So you have the inverse, and I'll place it. So what is the value I'm going to get? If you see, yeah. So I'm getting somewhere around 480 ohms. 1 by A in the bracket again. 1 by A means 1 is your voltage. Indicates your current. 1 by A. V by A is your ohms. So 480 ohms. So this is for a value of what? L equal to 100 nano. So let us try to make a note of that. So let me just make a note here. L, and here so for 100 nano we got L as 480 ohm, which is a low resistance. So that means I need to vary my L. Now this kind of experiment, it is not that you will be repeating it forever. See, these are the stepping stone for your next level of experiments. See, as and when we proceed and when we reach certain after a few sessions, we will not be working on to these things. We'll just fix up those W and L values directly, and then we'll moving forward. But these are the design steps that how you have to do. Let's say, for example, you want to design an amplifier, and in the amplifier you want to set up the W and L ratios, and to fix up those W and L ratios, this is how you are supposed to do in the initial stage. When you do in the initial stage and when you got the value of L, no need to repeat it forever. So that's how you can do all these kind of things. So let us try to change it. I'll change it to from 100 nano to, let's increase it to 400 nano. Let's see whether I'll just use new window option here so that I keep on getting different graphs. So this is my new graph. So this is my previous graph. This is my new graph. Send it to the calculator again. Take 1 by x of that, inverse of that, whatever option I'm going to get. Here now I'm getting, just I increase the value to 400 nano. I am getting the resistance as 7.25 kilo. So let me just, for L equal to 400 nano, 1.25 kilo ohm. Let's see, if I don't close this calculator, then again when I plot it, it will take the calculator option from that particular graph itself. So that's why I repeatedly keep on closing it. So let me just do it for a couple of more things just to give you a glimpse. So I'll just do it for 800. To calculator. Take the 1 by x of that. So if you see, it's 26 point or almost 26 kilo ohms. This is for which particular value? This is for 800 nano. So let me just write that also. For 800 nano, 26K. So that means if you see over here, the analogy is very straightforward. As L increases, the resistance is increasing. So where should I stop? So let me stop at a particular option so that I'll get the W by L ratio in an appropriate manner. So basically, what does that mean? See, I have chosen W is equal to 100. Where is my 10 micro. So basically I have chosen W equal to 10 micro. So when I do the W by L ratio, I'll try to fix up the value of value of L so that my resistance is also very high, and even the ratio whatever I'm going to get W by L. See, I don't want to have a ratio of W by L which gives, see, I want to have a WL ratio as some finite and constant number. I don't want to have a ratio in terms of 1.25, something like that. I don't want to have this one. I want to have some concrete value so that to remember that also will be easy. And Moreover, I'll be able to get my output resistance also should be very, very large. And if the resistance is very, very large, and when I use this MOSFET to build the current source, the current will be very, very large. So as of now, when I have W by L, W is fixed to 10 micro. Now L is at 800 nano. So if I just increase it to 1000 nano, or basically what is 1000 nano? 1 micro. Let's increase it to 1 micro. Let's do that. 1 micro, and then I'll run it. So that's my last graph. I'll send it to the calculator, open the function tab, and where is my 1 by x? Here it is. There you go. That is 36 kilo ohms. Okay, so just let me make a note of it. For this, it's 36 kilo ohm. So right now, for W equal to 10 micro and L equal to 1 micro, I am getting it as 36 kilo ohm. And to remember this, W by L as 10. See, this is what will be the ratio of W by L? Micro cancels. The ratio will be 10. So for W by L ratio of 10, that is for W by L equal to 10, what is my resistance? 36K. So even K is little bit on the lower side as compared to others other resistance value. Let's try to increase it from 1 micro to 2 micro, and then at last we'll fix up 10 micro and see what will be the value. So let's try to increase it to 2 micro. So 2 micro, then I'll again repeat the step. Take 1 by x, 103 kilo ohms. Fair enough. 103 kilo ohms. Let's do this. So basically I'm getting for W by L equal to, what was my W? 10 micro. L is my 2 micro. That means a ratio of 5 would fetch me 103 kilo ohms. Fair enough. So let's take one more resistance. Let's make it as 5. Send it to the calculator. Take inverse of that. 411 kilo. Oh, did I not change it? Oh, I changed it to 5. Okay. So for 5 micro, 411 kilo. So this was for what? 5 micro. Okay. And finally, let's change it to 10 micro. Again, if you change the W, now according to W, your L keeps on changing and you are going to get the different value of resistance. Okay. Now, let me do this. Now, this experiment is really important. Looks like it's very simple, and what exactly we're doing here, interpretation and your analysis. See, because when you do the bigger circuits, whichever bigger circuits you do, there you should not waste time in fixing up W by L. So for appropriate value of W, you are fixing up the L, and that well, how you are fixing, which is going to give you the maximum resistance. So just change it. Let me just rerun it. 1 by x. Now I'm getting 1.14 mega ohms, MA, right? So for L equal to 10, 400 and what is that? I'm getting 400, 1.14 mega ohms. So for 10 micro, 1.14 mega ohms. That means W by L equal to 10 micro by 10 micro, which is equal to 1. For a ratio of 1, I'm going to get 1.14 mega ohm. This is what I'm going to get. Now, this is the interpretation what I got. Now, there are multiple questions. I'll try to address that. But before that, let me just give you a simple things over here. I kept on changing the value of L here repeatedly for different values, just to show you that for each value, how it is going to reflect. Correct? Now I can do the same sort of analysis using what is known as parametric analysis. Now to do that, let us get into the results tool. Here there is something called as parametric analysis. Click on that. Now my parameter here right now is what? L. So I'll click on the add variable. I'll just double click. It will open this drop down option, and in that I'm going to choose L, and initial value of your here, whatever the value is you have given over here, that it will be taken over here. So basically what I'll do, I'll change it to 100 nano. Okay, so if I change it to 100 nano, here also it will reflect as 100 nano. So that's the initial value you have given over here. Here you will give the one value. Now I'm going to sweep it from here. What I did here, I initially manually I kept on changing the values from 100 nano, 200, 400, 500, 800 nano, 1000 nano, then 1 micro, 2 micro, 5 micro, 10 micro, right? So now instead of doing it manually, let's give the range over here and let the tool automatically do this parametric analysis. Now this is a very interesting thing which we can get it out from this parametric analysis. Let's try to do that. So first I'll do, and I'll sweep it for only 2 to 3 values, so that I don't want to mess it up. So let's try to sweep it. From where I want to sweep? From 100 nano, because initial value is 100 nano. I'm going to sweep it till 1000 nano, which is 1 micro. And step mode, auto means automatically it will break the steps. Linear means it will break the steps in terms of its exact values. Like for example, if I keep auto only, and if I give the total steps as 5, how the range of 100, or let me just change the range from from 100 nano till 1000 nano, it should break these range in terms of 5 steps, like 100, after that 300, 500, 700, 900, something like that. So I'll just make it 1100, so that the steps will be broken into equal stages. So if I keep it as auto, automatically the tool will itself take care of that breaking. If I give it as a linear, then basically it will break the steps equally in terms of 5 different steps. So that's how the stepping mode is being given over here. Okay, so I can choose any of them. So you can choose auto or linear. Better usually I keep it as auto. I'll leave the entire thing to tool only. So once that is done, I'll just run it here only. Run selected sweeps. So it will take some time, so that it has to run for all the corners. Yeah. So this is basically your different values. For different values, you got different options, right? Now see, this was the option. If you just expand this over here, if you see red graph, which is over here, so this is basically your ID versus VDS. This is not the R. Okay, these are your ID versus VDS. So if I close this, if I move it or copy it to new window, yeah, see, that's what it came over here. This L, it, because the graphs are multiple graphs, it won't show. See, usually the graph, whatever you plot of ID versus VDS in terms of frequency, it should look like this, right? But it is not looking like this here, because you have kept it multiple graphs. So it is coming like this. So what you can do, you can just send this, or you can just copy it to new window, and if you see that, it is exactly the graph which we were looking at. So the difference here is that in one go you got multiple graphs. So what I'll do, I can just send here only this to calculator. I'll send it to the calculator, and I'll take 1 by x. Sorry, it is, let me just close the calculator. Let me send it to the calculator. Okay, now let's take 1 by x and do that. I'm going to get this value. See, for this red graph, this is where I got it. To 480 ohms. That's what I got, right? For this particular value of graph. And here, what was the L? L is here, if you see, if you just expand, L was your 100 nano. 1 e raised to minus 7 means 100 nano. So you can have multiple graphs here. So here only can send, or the best way is what? You just right click on this, you keep on sending this, or you can move this to different windows. New window, I'll move it. It came here. Now here only you can see this graph is coming over here. Again, I'll just, if you move it, it will definitely, if it will move from here to the next window. If you copy it, the copy of the version of one version will be written over here, and one of the version will be copied. Like if you see the yellow graph, I'm just saying copy to new window. So it just copied into the new window, and the original version is still here. So you can just do that, and then from there you can keep on sending it to the calculator in one go, and you get the values. So that is basically the parametric analysis what we did over here. You can do either way. You can change it manually, because anyhow what these graphs are getting you an indication. Here it is an indication that you are just finding out the values of proper L for a given value of W, and what will be the maximum resistance. So that is where you are trying to figure out. Okay. Okay. Now there is one question. Now if the ratio of W by L is 1, if for W by L equal to 1, how did I got this as 1? I got this as 1 for W equal to 10 micro and L equal to 10 micro. You have to remember that. If the ratio is 1, and if W is 100 micro, L is also 100 micro, and then here also the ratio is also 1, isn't it? Now, will this ratio 1 and will this ratio 1 would give me same sort of R out? Basically, if you see here, L is your 10 micro. For L equal to 10 micro, you had already fixed up W equal to 10 micro in your MOSFET, in your tool. Here you had already fixed up the value of W as 10 micro. And then you kept on sweeping the value of L. And you reached the stage where you say that for a L equal to 10 micro, you got the value of resistance as 1.14 mega ohm. Now my question is, if L is 10 micro and W is 10 micro, the ratio is 1. Now to have the same ratio, I'll change my W equal to 100 micro and L equal to also 100 micro, and the ratio will again be 1. Will my R out be same? So that will be your first assignment, and this assignment involves some sort of iterations in the tool. So I'll try to float it right now. By 9 a.m. you'll be getting a sheet where you need to fill up that entire sheet by sweeping, by doing this sort of complete analysis, and you have to figure out for a particular value of which particular value of W by L, what would be your maximum resistance. And that chart would be very, very handy for you to figure out or to go for next level of experiments. Like basically what is my intent is, I'll just give you W equal to 10 micro, and I'm going to ask you to sweep it from 100 nano to, anyhow the nano values would be having a very lesser resistance. So I'll just, these experiments we just did it. Now what will be the value of R out? So you have to fill it over here. So this is basically one particular chart. So this will be your Now I'll change W equal to 50 micro, and you sweep the value again, L equal to 100 nano, 500 nano. This time we'll keep it as, rather than nano, we can, okay, let's that be nano also, 10 micro. Then we'll make it as 25 micro. Then we'll make it as 50 micro. I'm skipping the middle range. If you get a chance to add some more values, that's even better. I'll just try to float that. So what will be your R out? And similarly for W equal to, let's say, 100 micro. For L equal to different values. Let's say that L is again for the same similar kind of value, 1 micro. L equal to 2 micro, 5 micro, 10 micro, 20 micro, 50 micro, and then 100 micro. What is the value of R out? Now, why intention of this is, whenever you want to fix up the value of W by L, we will get automatically the ratios here. So again, here you are supposed to write the ratio also. Okay, W by L. So what will be the ratio of W by L? So what will be 10 micro by 100 nano? So the ratio of 10 micro by 100 nano would be, it is 100. The ratio is 100 here. If you do, see, 10 into, what is 10 micro? 10 into 10 raised to minus 6. What is 100 nano? 100 into 10 raised to minus 9. Okay, so 10 by 100 into, if I bring it over here, it will be plus 9, plus 9 minus 6, it will be 10 raised to 3, right? So basically this will be 10,000. So here two zeros goes and here two zero goes, 1 0 will be there, and answer will be 100. The ratio is here 100. Right, so you just write the ratio. So basically, henceforth, next time you fix up the value of W, and you can fix up the ratio of W by L, looking for the value of L over here and what sort of resistance you are expecting. So this chart would make you sure that whatever the value of L, W, and W by L ratio you want, based on that you fix up the value of R out, and you can use it appropriately in the experiments.